所以 Chapter 4主要是在讲说我怎么样把这个 Fourier analysis 从 periodic 的 continuous time signal extend 到 aperiodic 的 continuous time signal。所以主要的概念就是说，一个 aperiodic signal 其实可以看成是一个 periodic signal， 只是它的 period 趋近于无限大。OK？ 那在 Chapter 5我们只是对 discrete time 的 case 又重复再讲一次。OK？ So all of the concept is the same for the discrete time case as well. Okay. So here we're trying to extend Fourier analysis from periodic signals to aperiodic signals. Okay. So suppose that x of n is this aperiodic signal that we are interested in, right? So suppose that this is some general sequence with finite duration going from n1 to n2, right, and is 0 otherwise. So x of n can look something like this. Okay. Now suppose that x tilde of n is some periodic sequence that we generate by repeating x of n every integer multiple of the period capital N. Okay, so we take this x of n, we repeat it every integer multiple of capital N to get this x tilde of n. Okay. Now, as we let this capital N become larger and larger, right, eventually to infinity, then you can see that this periodic signal eventually becomes this aperiodic signal, right? So if you let this period become larger and larger, eventually to infinity, then eventually, as n goes to infinity, x tilde of n is just x of n. Okay? So this is the exact same idea as in the continuous time case. Okay. So suppose we look at this x tilde of n, which is a periodic signal. For periodic signals, we know that the Fourier series representation exists. So the Fourier series representation tells us that we can write this x tilde of n as a linear combination of these harmonically related complex exponentials, right? This e to the j k 2 pi over capital N times n, right? So 2 pi over capital N, right, we can view as this fundamental frequency omega naught. Okay? Right. And then how do we find the Fourier series coefficient? Right, this is the formula for finding the Fourier series coefficient. So we take 1 over n, the summation of x tilde times e to the minus jk 2 pi over capital N times n. Okay? So as we mentioned before, this is like taking the inner product between x tilde and this complex exponential in order to see how much of x tilde of n lies in the direction of this complex exponential. Okay? And one thing you need to be careful with is that we are summing over, one period, right? We're summing over any capital N consecutive integer values of k. Okay, so this could be, 1 to n, it could be 0 to n minus 1, or anything like that. Okay? All right. Now, here we're summing over capital N samples x tilde times e to the minus jk 2 pi over capital N n. Okay. Now, when you're summing only over one period, right, you could have replaced x tilde of n with xn, right? Because xn is exactly one period of x tilde, okay? And then you can extend the summation to infinity because, xn is 0 beyond one period, okay? So this summation, originally only over capital N consecutive integers, now is extended to infinity by replacing x tilde with x. Okay? All right. Now let us define this capital X as the summation of xn times e to the minus j omega n. Okay? So if you compare this with this here, then this summation is actually just capital X of e to the j omega at omega equal to k omega naught, okay? So this term here is actually x of e to the j k omega naught, where omega naught is 2 pi over capital N. Okay? So if you do replace the summation with this capital X, then AK is just 1 over N times this capital X at k omega naught. So if you plug this inside here, okay, if you plug this inside here, x tilde of n can be written as the summation over one period, 1 over n x times e to the j k omega naught times e to the j k omega naught n, right, which is this, okay? All right. And then we can write this 1 over n, right? If I multiply it by 2 pi, right, and divide it back, this 2 pi over capital N becomes omega naught, okay? So I multiply this by 2 pi and divide it back in the front, I will get a omega naught here, okay? So then what is this? What is this? Okay. So if you look at this particular value here, right? This is the function x of e to the j omega times e to the j omega evaluated at the point where omega is k omega naught, okay? So this term is essentially this function here evaluated at the point k omega naught, okay? And you can show, I'll probably have to show this tomorrow, you can show that this summation eventually converges as omega naught goes to 0, converges to a Riemann integral of this function over one period. Okay, over one period. Okay, so let's do that tomorrow. So let's continue from where we left off yesterday. Okay. So yesterday we were trying to extend this Fourier analysis of discrete time signals from the periodic case to the aperiodic case. Okay. So the key concept is the same as in the continuous time case. The key idea is to view an aperiodic signal as a periodic signal with a period that goes to infinity. Okay? Now, suppose that xn is the signal that we're interested in. Right? This is an aperiodic signal. And using x of n, we first construct a periodic signal x tilde of n by repeating this x of n at every integer multiples of capital N. Okay? So this x tilde of n is a periodic signal with period capital N that is constructed by repeating this x of n, right, at integer multiples of capital N. Okay. Now, as capital N goes to infinity, then this x tilde of n essentially will become x of n for all finite values of n. Okay? All right, so let's start by focusing on this periodic signal x tilde, which we know how to deal with. Okay. So for this periodic signal x tilde of n, we know that we can write it in terms of its Fourier series representation. All right, so this Fourier series representation is the linear combination of these complex exponentials at integer multiples of 2 pi over capital N, which is omega naught, okay? And this is summed over k consecutive values of capital N. n consecutive values of k, okay? And how do you find the Fourier series coefficients ak? You find it by taking the inner product between x tilde and the complex exponential e to the jk 2 pi over capital N times n, okay? So, this inner product you can write as the summation over one period, x tilde of n times e to the minus j k omega naught n, okay? Scaled by 1 over n in the front. All right. Now, since x tilde of n, is obtained by repeating, so if you, x tilde of n is obtained by repeating x of n every integer multiple of capital N, okay? So instead of summing over one period of x tilde, I can replace x tilde with x of n and then extend the summation to infinity, okay? Because x of n is 0 beyond one period, all right? Now we define this, the summation of xn times e to the minus j omega n, as the function capital X of e to the j omega, okay? And this is, we will see later, will be the spectrum of the signal, okay? So by this definition, this summation here can then be written concisely as capital X of e to the j k omega naught, all right? So using this concise representation, I can now represent ak as 1 over n, this capital X of e to the j k omega naught, and then taking this, substituting it back to the Fourier series representation. All right, so I take this, I substitute it back, I will get this expression here, okay? I'll get this expression here. Now, instead of writing 1 over capital N, right, I want to write this as 1 over 2 pi times 2 pi over capital N, which is omega naught. Okay? So by the definition of omega naught, right, this summation can now be written like this. All right. So this is where we ended yesterday. Okay. So now, what does this summation give us? Okay. So if you look inside each term of the summation, what we have here, right, this x times this complex exponential, right, what we have here is basically the sampling of this function, right, the sampling of the function x of e to the j omega times e to the j omega n at omega equal to k times omega naught. Okay? So what we have here is the sample of this at the point k omega naught. Right? Now let's suppose that this point is here. Okay. Okay, suppose that so this is the sample of this at point k omega naught. Okay, now here we're taking k over capital N consecutive integer values, right? So this can start from anywhere. So suppose we start from k prime. So this would go from k prime to k prime plus 1 all the way to k prime plus n minus 1. Okay? So if you take k equal to k prime, then this will be sampling at the point omega equal to k prime omega naught, okay? So suppose that this is the point. All right, so suppose this point is k prime omega naught, okay? Now when k is k prime plus 1, then we sample again at omega naught, distance omega naught later, okay? So suppose we take another sample here at k prime plus 1 omega naught, okay? And we can continue to take these samples, right, so on and so forth. Okay, and finally, we'll arrive at this sample here, which is at the point k prime plus n minus 1 omega naught. Okay? So for these capital N consecutive values, right, if you plug them in, then this part is essentially sampling at the points k prime omega naught, k prime plus 1 omega naught, k prime omega naught 0, k prime plus 1 omega naught 0, and so on and so forth, up to the last sample, which is k prime plus capital N minus 1 omega naught. Okay? Now, each sample is multiplied by omega naught. Omega naught is the duration between samples. Okay? So what this computes is actually the area of the bar from this point to this point. Okay? So we're actually summing over the area of this bar plus this bar plus this bar, so on and so forth, up to this bar. Okay? So we're summing over these capital N consecutive bars. Okay? Each one with duration omega naught. Now, what is omega naught? Omega naught is 2 pi over capital N. So when you sum over capital N of these bars, you're basically covering an area that spans 2 pi. Right? If you're summing over capital N of bars with duration omega naught, then you're basically spanning a range of 2 pi. So then what is this summation here? Right? This summation is the summation of the area of all these bars, which gives you an approximation of the integral of this function over a 2 pi range. Okay? Now, it's easy to show that this function is actually periodic with period 2 pi. Okay? So you can easily see that because, let's say for the term e to the j omega n, right? If you take omega plus 2 pi, substitute it inside, you essentially get back e to the j omega n. Okay? So this complex exponential, because n is an integer, is periodic with period 2 pi. Now, similarly, you can show that this is also periodic with period 2 pi, because if you substitute omega plus 2 pi inside, right, what do you have? You have omega plus 2 pi here, which when multiplied with the integer is the same as omega n. Okay? So we know that this thing is periodic with period 2 pi, and so is this. Okay. So what this summation is basically an approximation of the integral of this function over one period. Okay. Now, as capital N goes to infinity, okay, as capital N goes to infinity, in which case x tilde of n converges to xn, okay? So as capital N goes to infinity, omega naught goes to 0, right? So these bars become narrower and narrower, so you get a better and better approximation of the integral, okay? So eventually, as n goes to infinity, okay, or omega naught goes to 0, this summation eventually converges to the Riemann integral of this function over one period, 2 pi. Okay? So this is over any 2 pi range. Okay. Right, so that gives us the Fourier transform in the discrete time case. Okay? So in this case, this x, capital X that we defined, is the discrete time Fourier transform. Okay, sometimes we write, DTFT for short. Okay? And therefore, you have this discrete time Fourier transform pair. Right? So this equation on the bottom, right, gives you, helps you identify what is the component of the signal at frequency omega. Okay? And this equation above tells you how to synthesize the original signal by taking a linear combination of all of its frequency components. Okay. So going from periodic to aperiodic, right? In the periodic case, the signal is represented by a linear combination of these discrete frequency components. Okay. But as capital N goes to infinity, right, as the signal gradually becomes aperiodic, you will not be able to reconstruct the signal using only discrete frequency components. But eventually, you would need to use a continuous range of frequency components. Okay? So that's the only difference here if you compare it with the periodic case. Okay. So since this helps you synthesize the signal using these frequency components, we sometimes call this the synthesis equation. Okay? And since this equation helps you extract or helps you analyze the frequency component of the signal at different frequencies, therefore, this equation is often called the analysis equation. Okay. Now, another thing that's worth mentioning here is that you can see that in the discrete case, we're representing the spectrum as a function of this e to the j omega. Whereas in the continuous time case, for continuous time Fourier transform, we use the notation x of j omega. Okay? So whenever you see this, you know immediately we're referring to the continuous time case. And if you see this, you know we're referring to the discrete time case. Okay. All right. So I mentioned that, you know, when going from periodic to aperiodic, right? The difference is that for periodic, you're summing over discrete frequency components, whereas for aperiodic, you're integrating over infinite frequency components, right? A continuous range of frequency components, okay? So this is comparing with the periodic case. Now, if you compare with the continuous time case, right, the difference is that for discrete time, the spectrum is periodic, so you're integrating over only one period, whereas in the continuous time case, you're integrating over the entire, you know, range of omega from minus infinity to infinity. Okay? All right. Now, another thing is that, you know, here, when you look at this analysis equation, you have this summation to going to infinity. Okay, so when you have something going to infinity, you're always concerned with, you know, the convergence of this summation. Okay. Now, for this to hold, right, you basically need the signal x of n to be absolutely summable, or to have a finite energy. Okay, so these two conditions, right? Either one of them is sufficient for the existence of its Fourier transform. Okay. Now, another thing worth mentioning is that, as we just mentioned, this discrete time Fourier transform, right, is periodic. Okay. So when you say that this signal has a low frequency component, right? If you say that this, if you say that this signal contains mostly low frequency components, then you will see a spectrum that is concentrated around 0, but this will be repeated at every, you know, integer multiple of 2 pi. Okay. Now then, what do you refer to as a high frequency, you know, signal, right? So instead, if you have a signal whose spectrum is concentrated around pi or minus pi, then you say that this is a high frequency signal, okay? Because for this discrete time, we're only concerned with the spectrum over a 2 pi range, typically going from minus pi to pi. Oh, sorry. Okay? So if you look only within this 2 pi range, it would be more clear when you what you refer to as low frequency and what you refer to as high frequency. Okay. Okay, so I went a little bit slower through this part just to, you know, make sure that the concept is clear. Okay, so when you go back, I would encourage you to, you know, think more about the difference between the discrete time case and the continuous time case, and also between the aperiodic case and the periodic case, okay? All right. So the rest are just a few examples, okay? So here we have a discrete time, right, xn equal to a to the power n times this unit step function for a less than 1, okay? So this is basically, this is analogous to this single-sided decaying exponential in the continuous time case. Okay. All right, so what is the spectrum of this signal? Okay. So by applying the formula before, we have the summation, and from minus infinity to infinity, a to the power n, un, e to the minus j omega n. Okay. Now un is 1 for n that is greater or equal to 0. So this limits the summation for n from 0 to infinity, a n e to the minus j omega n. Okay. So this is basically the sum of a geometric series, right? This is the sum of a geometric series. So we can use the formula for the sum of a geometric series to get, right? So this is basically 1 over 1 minus a times e to the minus j omega. Okay? Right. So this is the spectrum that we get, right? And here we have, here we can visualize what this spectrum looks like by plotting out the magnitude and the phase. So what you have here is the case where a is greater than 0. And on the right-hand side, you have the case where a is less than 0. Okay. So how do you see this? Right. So for example, suppose we focus on the magnitude. So the magnitude, okay, is just the square root of 1 over 1 minus a e to the minus j omega, 1 minus a e to the j omega. Okay? So this is square root of x times its complex conjugate. Okay? So this gives you 1 over square root 1 plus a squared minus 2a cosine omega. Okay. So this is, similar to one of the examples we did before. Okay, so if you look at this, suppose that a is greater than 0. Okay, and looking at this cosine, when omega is 0, cosine 0 is 1, right? And as omega goes from 0 to pi, right, it gradually becomes minus 1. Okay, so cosine omega decreases, becomes smaller and smaller as omega goes from 0 to pi. Okay, so when this becomes smaller, the denominator becomes bigger, and the whole thing becomes smaller. Okay, so if you look at the magnitude here for a greater than 0, you have a peak at omega equal to 0, and then you start to, decrease as the frequency goes towards pi, okay? And similarly on the other side, right? And again, we can focus only on this 2 pi range because beyond that, it just, repeats itself, okay? Now, on the other hand, if a is less than 0, then as omega goes from 0 to pi, this instead becomes larger and larger. So when a is less than 0, you have the lowest point at frequency 0 and peaks at high frequency. Okay? So this result actually is not surprising because if you observe this signal, right, when a is greater than 0, then a to the power n is just this decaying exponential, right? It's a smoothly decaying exponential, okay? So it doesn't have drastic changes in the amplitude, so it's mostly low frequency. But if a is negative, then as you increase n, you oscillate between positive and negative values, okay, as it gradually decays. So because you have this oscillation between positive and negative values, therefore you have a very high frequency component. Now in the next example, right, this is for a single-sided decaying, this is analogous to this single-sided decaying exponential in the continuous time case. Right? So in the continuous time case, we also looked at this double-sided decaying exponential, right, which is analogous to this in the discrete time case. Okay. So for this, what is the spectrum? Okay. You can write this as summation over n, a to the absolute value of n, e to the minus j omega n